Thank you very much. I thank the organizers for inviting me to speak this symposium, and I'm very glad to be in Kyoto. Here's an outline of what I hope to cover. First, I would like to talk about technology, and then the connection with physics, the unreasonable effectiveness of mathematics and physics. And in this talk, I will talk about my experience at Bell Laboratories. So I will talk about Bell Laboratories, and then I will talk about mathematics in Bell Laboratories, and then I will talk about the connection with computation in the future, particularly quantum computers. So this talk is about, I did both pure and applied math. This talk is about the applied side, what mathematicians do in industry and applied areas. It's based on my experience at Bell Laboratories, and at the time I was there, Bell Labs was the R&D part of American Telephone and Telegraph Corporation, or AT&T. It is said Bell Labs worked on incremental improvements to the communications network while simultaneously thinking far ahead towards the most revolutionary inventions imaginable. And so now we have universal communications by smartphones. So the cellular smartphone is a complicated, possibly most complicated product of technology used by nearly everyone. It is a two-way radio and a computer. So the latest smartphones contain 2 billion transistors, and in the latest generation, the transistors are 14 nanometers across, which is only about 70 silicon atoms across. And what has math got to do with the working of the smartphone? So let me talk about making a sound or video phone call. So speech is converted by the microphone in the cell phone to electrical signal. The electrical signal is converted to a digital signal, zeros and ones, and then various digital mathematical operations are done on it. In this talk, I have lots of italicized words, and these words can be looked up in Wikipedia because I only have time to sketch. So the tasks that have to be done inside the phone, the electrical signal is sampled, it's quantized into zeros and ones, then it is compressed to remove redundancy. If you send a video signal, it's very large, and for each video frame, you only keep track of what changed from one frame to the next. That's compression. The digital signal then may be encrypted to ensure privacy, and then finally, it is coded with codes to correct errors so that it is received perfectly at the other end. The digital data is then sent by modulated radio waves at the microwave range to a cellular base station or a wireless router. And modulation here means that the wave is periodic, it has a carrier wave, and we modulate it, we put little fluctuations in it, and that keeps that's where the data bits are encoded. So here are two pictures. You have your wireless computer. It is sending a radio signal to the wireless router, which is doing some of the coding and encryption. And then it is sent over a modem, which means a modulator and a demodulator. Modulator when you send it up, and demodulator when you send it back. I have a second picture here. If you have a cell phone and you're driving in a car, then the regions are covered by cell base stations, and your radio signal is sent to the nearest cell tower that has the frequency that you've been assigned. And the cell towers are assigned different radio frequencies so that many people can use them. And when you move from one station, the area covered by one station, to another cell, then you have to be reassigned a frequency and reassigned a new station, and this all has to be done quickly, and the transistor technology is used for that at the base stations at the bottom of the cell towers. If you send it over the internet, The data is grouped into packets. The packets have headers that tell you how to send them. So the message is broken into little pieces, and they are sent in different pieces across the internet by different routes to the other end. And at the other end, they have to be reassembled into the message, which is then decoded to give you the phone signal at the other end. The main point I want to make in saying all this is that a whole lot of mathematics is used in the process of making a phone call on a smartphone with the coding and encryption, and it's needed to make it work. But it's hardwired in there. A lot of this mathematics has been available for a long time. It was developed at earlier times, but there was no way to do the switching fast enough to get an actual product that people could use. That has come from the revolution in transistor technology, leading to these integrated chips with very large number of transistors, the microprocessor, and the fact that the transistor is basically a switch, and it can switch very, very fast. And because of this extremely fast switching, we can now do all the mathematics inside the phone to make it work. AT&T tried having a picture phone in the late 1950s, and it was just very slow. But now with these chips, we can do much faster. And the second key material ingredient is that we can now transmit data in large quantities using optical fibers. So an optical fiber is a laser glass fiber, very pure glass, slightly larger in diameter than a human hair. It's the backbone of the internet. A single optical fiber can carry 7 million telephone calls. With reference to the first talk today, these layered fibers have a central core, and then they have a second layer on the outside that has a different refraction index, and it worked with the same principle as the core of the Earth. The outer layer forces total internal reflection of the light waves inside the original thing, and it traps it so it goes along the fiber. So my first point was that that's where math developed over a long period of time, was used in this product partly in making it work. The second thing I want to discuss is mathematics and physics and the unreasonable effectiveness of mathematics. So this is a paper by Eugene Wigner, a physics Nobel Prize winner, called The Unreasonable Effectiveness of Mathematics in the Natural Sciences, which you can easily find with Google. And he said in this paper, the world is of baffling complexity, and the most obvious fact about it is that we cannot predict the future. But you can in very limited special cases, laws of nature. So a law of nature is a law that predicts future behavior. It's mathematical in nature, quantitative and precise, and it applies in limited circumstances. It also says that certain other variables are irrelevant to the prediction working. And picking out and discovering these laws amidst the chaos of experience is not obvious. And the scientific enterprise aims to find and extend the range of these laws to wider domains. So Wigner asked, why are the laws of nature described accurately by mathematical equations? So I can take Newton's gravitational law, that two particles attract each other by the product of the masses times the gravitational constant divided by the square of the distance. And he said, if it applies on Earth, could it apply to the moon? And he applied it to estimate the moon's motion, and he calculated it with accuracy to 4% in the Principia. But now the gravitational law is repeatedly tested with more precise experiments, and it's found to be accurate to 1 part in a million. Why is that? Why is it so precise? And Wigner's answer is the enormous usefulness of mathematics in the natural sciences is something bordering on mysterious, and there's no rational explanation for it. It's just something we found. So now I want to give the example of electricity and magnetism because that's the basis of microwave transmission for phones. So in 1820, Ørsted discovered that turning on an electric current in a wire deflected a compass needle. So he turned on the wire, and the compass needle went to be perpendicular to the wire. And it was an amazing discovery because no one had any idea at that point that electricity and magnetism should be related at all. And following his discovery, it was reported to all the neighboring countries, and the Englishman Michael Faraday was an extremely good experimenter, and he did researches on electricity, and these were collected and published, and they reported all of his experiments, the ones that worked and the ones that did not work. It's useful to know what doesn't work, and I want to mention his discovery of electromagnetic induction, which is that a moving magnetic field induces an electrical current in a nearby wire. And he described induction by using lines of force. He was not a mathematician, so he did not describe it with much mathematics. Another thing he found was the Faraday cage, which is a method to shield an area from electromagnetic radiation from outside. If you put in metal walls, the outside radiation will induce currents in the metal walls that cancel out the field inside. You can also use it on the inside as well, so that you don't have things you don't experience the field outside. The Scottish physicist James Clerk Maxwell in the 1870s studied everything known about electricity, and he wrote a book on it called A Treatise on Electricity and Magnetism. And he formulated differential equations to describe the phenomena found by Faraday, induction, plus results of his own experiments. So he wrote down 20 partial differential equations that described how the field induces forces locally, and the equations then say how the field will change over time as you progress in time. That is a prediction. If the field is this now, it will evolve according to the equations. So this is the first field theory, which in the current standard model of physics is the U1 theory. He found that, so he was forced to describe the phenomenon with these equations, and he then discovered the equations had solutions of the following form: transverse electromagnetic waves of oscillating electric and magnetic fields traveling at a constant speed. They could have any frequency. They were simply a solution of the equations that was predicted. And electrical measurements of the electric constant showed that this speed was close to the known speed of light. And so therefore he suggested that visible light is an electromagnetic wave. And this is completely strange, that light which goes into our eyes has actually got oscillating electric and magnetic fields in it. I mean, it's an unbelievable thing, and I will at the time, and I will show you the evidence from Maxwell's book. So on the left-hand side, you see the estimates of the velocity of light computed by experiments in air and distance of looking at planets and so on. And on the right-hand side, you see the speed of the electromagnetic waves as computed as a ratio of certain electrical constants. Completely different experiments. And you will see that the speed in meters per second is extremely close. And he says it's manifest the velocity of light and ratio of units are quantities of approximately the same size, within a few percent. We don't know at enough accuracy to tell. It's hoped that further experiment will resolve this. So what I'm going to say is that Maxwell's equations turned out to be one of the most extreme cases of unreasonable effectiveness. So Heinrich Hertz, a German physicist, A few years later, his advisor Helmholtz said, please test Maxwell's theory of electromagnetism. Is light an electromagnetic wave? I should say that Maxwell died, so he was unable to do the experiments himself. In 1887, Hertz found a way to generate electromagnetic waves of length about a meter. So these are radio waves, and he did it in a big room, and he put an antenna with an oscillator at one end and a reflecting plate at the other end, and this will set up a standing wave if the frequencies are right, and then he detected it using a little detector with a spark gap, and he moved around the room, and when he was at the crest of the waves, he would get a spark, and when he was at the trough of the waves, he wouldn't get anything. And he also tested all the other diffraction and refraction and other experiments on these waves to show that they behaved like ordinary light. And about his experiments, he said, it's of no use whatsoever. This is just an experiment that proves Maxwell was right. We just have these mysterious electromagnetic waves that we cannot see. And he was so wrong about that. So now I want to say about the electromagnetic spectrum that they occur at various frequencies. The oscillations are measured per second in hertz. The relation of frequency and wavelength is that frequency times wavelength is equal to the speed of light in meters per second, which is 299,792,458. This is the definition of what is the length of a meter. And why this visible light has wavelength, very short wavelength, 5 × 10⁻⁷ meters. And infrared is longer waves. It is the frequency used in transmission on optical fibers. The microwaves are still longer. They are the frequency used in radar and cell phones. Radio waves are still longer. So I have this thing from the internet, so the visible light, the very short wavelength, infrared, radar, FM, TV, short wave, AM radio at the longer wave things. We simply can't see these rays, but as Maxwell predicted, they exist at all frequencies. Many cell phones work at an assigned microwave frequency between 1850 and 1990 megahertz, which is about 15 centimeters. This is very close to the frequency of a microwave oven, which has wavelengths 12 centimeters. So why don't you get cooked by your cell phone or laptop computer? And the reason is the power used is extremely low. So here's a microwave oven. I would like to explain that a microwave oven has metal walls and a metal mesh across its front entrance, and it acts as a Faraday cage, trapping the radiation inside. The mesh is necessary to stop the microwaves from getting out. The holes in it are significantly smaller than the wavelength of the microwave radiation. Visible light, which has a much shorter wavelength, can go right through the holes, and you can see it on the outside of the oven. The walls of the oven reflect the waves generated in there, and they set up a standing wave inside the microwave oven, very similar to Hertz's experiment. At certain places, the waves reinforce, and you get high energy, you get a hot spot, and in other places inside, the wave cancels out, and you get no heating. The rotating turntable at the bottom of the microwave oven is necessary. It moves the contents around through the hot spots so that they will be evenly heated. So my excuse for including this is that the heating principle was patented by Bell Labs in 1937. They were using microwaves to manufacture certain phone equipment that needed to be evenly baked and evenly heated. Now I want to talk about Bell Laboratories rather quickly. When I started work at Bell Laboratories in the early 1970s, it was a It was a telephone company that served almost everybody in the United States. It had 1 million employees. It was called the Bell System, and it combined production at Western Electric, the manufacturing part, research and development at Bell Labs, and distribution of phones to everybody served by the local phone companies. As a monopoly, it was regulated by the US government, which controlled its rate of return. And the goal of the AT&T was to establish universal communication services. And this is now what we have. We have universal communication services across the entire world via the internet, which is the development of all the things that it did. So it has achieved that mission, and in so doing, it has changed the world. And it also changed itself. The monopoly was broken up into pieces. During this period, AT&T, by the regulations, was allowed to have steady funding to support the Bell Laboratories, and therefore it established a very large, stable group of researchers and developers. It had a budget that was 10% research and 90% development. So the research part was very small. And here's a picture of Bell Labs. It was located originally in downtown New York City, in Manhattan, until '52, and then it moved out to New Jersey. This is the main location in Murray Hill, New Jersey. I worked in one of the buildings on the left. The buildings on the right had all of the labs, the chemistry, the physics, and the material science, and the ones on the left didn't have the labs. Bell Labs had a unique design. It was designed to get researchers to work across fields. It was designed to encourage interaction across all the people in different disciplines to break down communication barriers in order to get problems solved, to get engineers, physicists, material scientists, mathematicians, statisticians, lab workers, all to communicate together to solve problems. So, for example, it was required there that you had to address everybody by their first name from the first day that you worked there. So at some point I had to deal with Arno Penzias, who was the head of research, who was a Nobel Prize winner, and I had to go into his office and I had to call him Arno, and it scared me. Workers in all different disciplines had offices mixed together so that you would run into people in different disciplines with the doors kept open. It had long, straight corridors allowing random interactions through meeting in the hall. I would like to say the work culture is that different scientists think differently because of their training. So as a snapshot, engineers want to build. They want to make things that work. They want to use the existing materials to make things that work. So the existing materials are the constraint for them. Physicists want to predict. They want to describe the real world accurately. And for this, experiments are the test of predictions. And at this time, Bell Labs had the best groups in condensed matter and materials in the world working there. What do mathematicians want? Mathematicians want to prove. They want to find rigorous proofs of ideal problems with complete certainty. And only after that do they want to find out how does it apply to the world. Well, I don't know if this is quite accurate, but that's Bell Labs made many important discoveries that have changed technology, and I want to mention 3 of them plus an application. So the first is the transistor. That was invented in the 1940s by Bardeen, Brattain, and Shockley. They received a Nobel Prize for it. Bell Labs sought it as an electronic switch to replace telephone switching, to replace mechanical telephone switching. The solar cell was invented in 1946, a practical version you could manufacture in 1954. They invented it in order to supply powers for amplifying telephone calls that were in the middle of the desert. They wanted to put a repeater on a telephone pole and not have to drive a long distance in to replace it. The laser was invented. This acts as an optical amplifier at optical wavelengths. It, of course, has many applications, but it is used in the optical fiber network, the backbone of the internet now. The application is the cosmic microwave radiation, the Big Bang radiation observed by Penzias and Wilson in 1964, for which they received the Nobel Prize. Why did they do this study? Because it was done to determine the background level of microwave noise that would interfere with AT&T's microwave telephone calls sent by satellite. That was why this study was done. In each case, it was done for a telephone application. So with regard to switches, here's a telephone operator about 1900 with switches for plugs to plug in calls between different people. Here's a picture in 1937. This is a picture of a mechanical crossbar switch. So the switches now work by electrical power that will shut a mechanical contact to complete a telephone circuit. They had buildings full of these things. After that, we go to the electronic switching. So electronic switching was introduced using transistor technology in the 1970s. This is a building in downtown New York City. It has no windows. It has this futuristic look. Inside it are a very large collection of switching machines for handling switching on Manhattan Island. I want to say something about my work at Bell Labs before going to the Mass Center. So first of all, I got a degree in 1974 in absolutely pure mathematics and number theory, actually doing stuff related to what Professor Sunada just talked about. But the job market was very bad, and I voted with my feet, and I took a job at Bell Labs, and not in research. I took a job in development area. So for 6 years, I worked in a development area doing operations research and applied economics. I did that because I had summer experience doing that. After that, I worked in the Math Research Center, and I worked sort of in 5 years blocks. I worked on computational complexity and cryptography, that's computer science. And then I worked on optimization related to the Karmarkar algorithm, and that's operations research. And then I worked on the theory of wavelets, and that is signal processing. And then I worked on the mathematical theory of quasicrystals, and that's condensed matter physics. So I did a lot of applied things. And then I went to the University of Michigan, where I again did number theory. And I made connections across different fields. So finding connections in the research area, finding connections between different fields can lead to discoveries because it can enrich both fields with new ideas. An old idea in one field can instantly become a new idea in the other field, and vice versa. Now I want to talk about the Bell Labs Math Research Center. The research center it had about 50 people. Its role was to develop new results in mathematical areas related to the business, and management gave freedom to some people to work for years on long-term projects, and it had other people who were working on very applied areas. So at the bottom, there's this division of labor. It included people with different skills, from the most theoretical to the most devoted to applications. And the degrees were not all in math. They were in physics, electrical engineering, operations research. So it had two pieces: the developing the new mathematics to conceptualize general methods, and to carry, there's theory, and to carry out processes, that's algorithms. And on the consulting role, it was to help out AT&T with their business, and also to help out all the other research areas at Bell Labs in solving their problems when they would consult the mathematicians. So maybe I should say something about, we heard from Professor Mori that there is no dividing line between pure and applied math. And I would say that's so, but I would like to say that pure math, you investigate new internal structures for their own sake. you find these structures, you find connections between these structures, you find new methods, and the motivation of the people to do this is beauty and curiosity. And when you first find these things, it is not clear what practical use they have. But once they are found, math has found true things. They are like little widgets. And they can go into the mathematical stockroom because you now know that a problem in this area, this theory might apply to it. And what does applied mathematics do? Applied mathematics is goal-oriented problem solving to solve applied problems. And you can say it is to find a use for widgets that have no use. So adjusting and specializing the widgets to a more useful form for applications. And the applied widgets also go in the stockroom. I'm now going to, because of the interest of time, I'm going to skip some slides to just say that Bell Labs invented entirely new disciplines or developed them. The first is queuing theory, which is the theory of waiting lines, which is now enormously important in analyzing systems like the internet. It analyzes waiting lines of calls so that you can guarantee that long-distance calls can go through with high probability. There are the great theories of Shannon, information theory, and coding theory. He developed a quantitative measurement of information as entropy in bits, and he found a theoretical limit on the rate of reliable transmission over a channel that makes errors, which indeed all the communication channels we use make errors. He showed the theoretical existence of error-correcting codes to detect and correct errors to achieve that limit. You take your signal and you put redundancy in it that are checks on the signal that allow you to correct the errors. This is coding theory. And his result was a theoretical result like Professor Tsunada mentioned. He proved that these codes exist, but he did not give a way to construct them or find a good way to encode and decode them. So the error-correcting codes introduce redundancy of message strings using check bits. As Professor Mori mentioned, algebraic geometry has been used in constructing interesting error-correcting codes. And the last 70 years have been spent in finding good codes that have fast encoding and decoding to get close to the limit that Shannon allows. And these good codes require large computer calculations to do the coding, and they were not practical. The really good ones were not practical until we have the enormously fast chips that we have now. So there are applications in space probes for sending pictures back from Pluto where there's a lot of noise, and CD players and smartphones. The role of the Math Center on the consulting side is hearing problems from other areas and helping to formulate them, and for a formulated problem to supply a yes or no answer, which is a yes answer is there are mathematical methods that apply to the problem, and you can form a team of people to try to do applied mathematics to get a solution based on these methods. Or the answer is no, mathematical theory is unknown for this kind of problem, or the methods that are known are too slow to solve it. There's nothing suitable, so maybe you should change your approach to the problem you have. And in both cases, this leads to new mathematical research. In the first case, the yes case, you do new applied mathematics, and in the no case, you do new pure mathematics to maybe answer this question. I want to do two things. I have a consulting example, which is the business problem was that cellular base stations installed by AT&T were required by regulations to replace a chip in it with a new chip for signal processing, and that the designers did not realize that this chip had an incompatibility with some other signal processing thing in the box, and it wasn't detected right away. It started dropping people's cell phone calls, and the problem showed up after a few months when enormous numbers of these stations were installed. And these boxes are built extremely solidly. They have many screws, and to fix it required bringing them all back to the factory, taking them all apart, and replacing the new chip. And the estimated cost for the hundreds of thousands of these things was $100 million US. So here's a cell phone tower made to look like a palm tree. That's the antenna. That's a real palm tree behind it. The base station is in this little building. A Math Center member found a software solution to the problem. He found a way to adjust the signal somewhere in the box that was outside the box on a plug-in chip. So they could simply replace the chip on the outside of the box, and they didn't have to take the base stations back to the factory. He found a way around the problem. And this particular person was an electrical engineer who actually had something to do with the original design of the original thing. So that's the reason he was able to do it. But it really pleased our bosses, and it justified the salary of the entire Math Center for that year and more. Now, because of the time, I'm going to skip fast through the Karmarkar algorithm. This was a new method in optimization to solve linear programming problems. It has many commercial applications. It's important in many business applications, such as airline companies for scheduling planes and flight crews. And because of the important economic applications, it was announced on the front page of the New York Times in 1984. And I will say only the method is you're trying to get to one corner of a polytope, and the old method crawled along the edges of the polytope, and the new method tried to go right through the middle with a differential equation. This picture is 2 dimensions, but the actual problems are 1 million dimensions, so they cannot be displayed. At this point, the interior point methods 30 years later are now routinely offered in linear programming packages along with the simplex method. It turns out both methods are actually good in different situations. And they have proved useful in nonlinear problems. That is the important development that came out of it. I would like to mention that there is a connection of this algorithm with pure math. It turns out the trajectories of the differential equation are algebraic, so there's an algebraic geometry structure. And there's also a dynamical system which has the remarkable property that it's an integrable Hamiltonian system. Now that has not been exploited because that is pure math, and it went in exactly the wrong direction. And the wrong direction was for the research for the first 10 or 15 years was to speed up this algorithm and find out when it worked as efficiently as possible. But the pure math may still pay off later on. Now I would like to quickly say something about quantum computing. So computers are getting so small now, the chips are getting so small that there are only a few atoms across for transistors. So we are at the limit where quantum mechanics, which predicts the physics, which says there's an irreducible amount of noise on this low level, and in the current computers you try to cancel out the noise and make it and the question is, can the laws of quantum mechanics be harnessed to make a faster computer allowing smaller things? The idea is not to fight the disturbances that quantum mechanics predicts, but to accept them and to try to use them for computations. And Richard Feynman said about quantum mechanics, I think I can safely say that nobody understands quantum mechanics. It has something non-commutative in it that's just, it does not, the rules of how it operates, the mathematical equations are crazy, and you understand them in mathematical terms because they say that things can be particles and waves at the same time, and that's is very different from classical behavior. So the new computational resource is entanglement, which are quantum correlations of behavior. And a big shot in the arm in quantum computers came from a development in the Math Center when Peter Shor showed there were problems that that are quickly solvable on a quantum computer that are not known to be solvable on a current digital computer. These are factoring and discrete logarithm problem. So the factoring problem we saw, if you have a large integer n, it's not prime, can you split it into a product of 2 numbers, a and b? Nobody knows how to do that quickly, at least not for 200-digit numbers. The problem of multiplying 2 numbers and making n, that's easy. However, the difficulty of the factoring problem and the discrete logarithm problem are used in standard internet encryption methods, and these algorithms show that quantum computers, if they could be built, are a threat to internet commerce. So that it made a tremendous interest in developing quantum computers, and the question is, can they be built? And there's a technical difficulty, which is that quantum computers that use entanglement are sensitive to external noise. You have to cool them close to absolute zero, and the collapse of the wave function destroys quantum computations. So a partial solution was then found by Peter Shor the next year. He showed there did in fact exist quantum error correcting codes. You can't measure a bit to see if it's an error, because then you destroy the bit and you can't fix it. These codes correct errors in some indirect way without looking at the bit you care about. But this removed the last engineering restriction to prevent building a quantum computer, at least in theory. And as of this year, a working ion trap quantum computer with 5 ions has been built that could factor 15. That's 3 times 5, using the Shor's method. And this method is described as scalable, so certainly they're going to try to build bigger ones. And the question is, are they going to work? This is extremely interesting, because a quantum computer, if it could be built, it's a new experimental test of the laws of physics, far outside the known range for testing quantum mechanics, the linearity and superposition of quantum mechanics, if they could build a big one with a lot of entanglement. And so, will the laws of quantum mechanics remain unreasonably effective when we go to this point? And certainly if they can be built, prizes will be given. We don't know, and the only way we will know if somebody builds one and it works. Because if it can factor a 100-digit number, that's a proof that it's working. The way we know the laws of physics are working is your smartphone works. Right? This is the unreasonable effectiveness of mathematics in the physical sciences. So I want to conclude with 2 comments on computers and mathematics. The increase in computing speed and power has happened so fast that we have not had time to figure out the applications. Math research is an experimental science, and computers are a wonderful tool in making such experiments. When you do research, you first find out things you believe are true, and then you try to prove them. And there are great opportunities ahead, new fields involving math and computers, and among this, using computers to check mathematical proofs. Since proofs are what mathematicians try to do, and some proofs are so long now. So mathematicians, others that are things that will come, mathematicians can work in larger groups because they can communicate across the world. There are entirely new theories being developed in computational geometry, topology, biology. We already heard that artificial intelligence, will computers get smart enough to do new mathematics? We don't know, but already they can do some things. So Doron Zeilberger has a computer that has written quite a number of math papers, which have been published. You can find his website. So this is it. Besides describing applied mathematical work, I gave this talk to honor Bell Laboratories for the wonderful environment it provided to me and so many others for 30 years. Thank you for your attention.